Okay. Sorry to the listeners on the call. So
Yeah.
I think the mic is working, so hopefully everyone has heard me in here. But my apologies to the Zoom listeners. So I'm talking about dictionary learning. This problem is that very similar in many respects to simple sparse reconstruction. In many other respects, very different. Lots of interesting mathematical challenges associated with understanding the performance of these algorithms in practice. But the upshot was that before we had deep networks, we could use deep learning or dictionary learning to do all types of things, process high dimensional data, denoise it, do super resolution, what have you, interesting applications. And things worked pretty well. And we could understand pretty well mathematically how these algorithms were working as well. But of course, in the modern era, we don't just want to process linear signals. We want to learn to represent signals in the physical world. And we're very ambitious. We want to learn how to segment anything. We want to do things like tracking everything everywhere all at once. And maybe we even want to learn how to interact with the physical world using agents and things like that that can really perceive and operate on what they're perceiving. So to do that, you really have to start coping with essential nonlinearity in the data here. It's not enough to just model everything as being sparse in a linear dictionary. You really have to cope with complex nonlinear structures of motion, illumination, objects moving around, just speaking about perception here. And when you do that, you start to need algorithms, networks, representations, really, that are deeper, that can cope with these forms of nonlinearity, learn expressive representations that can be used to solve various downstream tasks, perceive and interact with the world. So to me, I just want to sit on this a little bit because even though I'm working a little bit or maybe a lot on deep learning these days, I still kind of consider myself as being a theorist. And so I very naturally want to try to think about what we're doing with deep representation learning in terms of what we have before and sort of the general picture of the mathematical kind of framework for high dimensional analysis, high dimensional data analysis. And I think it's uncontroversial to say that when we think about theory in this modern setting of high dimensional data analysis with deep networks, understanding representation learning is the most important and completely open as well theoretical question. And the reason it remains completely open, I think, maybe this is just my perspective, but it's because it's kind of maybe a little bit unclear a priori what the best way to make progress on this very general question is. So what I'm presenting on this slide here is my kind of my personal view, and it's by no means an exhaustive sort of characterization of how one can do theory in this setting. But I kind of think there are two, maybe at least in the stuff that I've worked on, two different ways that are sort of notable here that one can think about doing theory to understand deep representation learning, especially as it works in practice at large scales for highly nonlinear data from the physical world. And one of those approaches is kind of top-down. And this is a little bit mirroring a lot of what we see when we're studying mathematical problems in statistics, signal processing, other fields like the sparse reconstruction, for example, that we talked about before. So we're sort of thinking as deep networks, deep representations, maybe models for data in some settings, as kind of like things that, in some sense, nature has provided to us. They just exist. And maybe we've heard about them from our colleague who is actually training these models, what have you. But the idea is that given these objects and maybe these models that we develop for them, for deep networks, feed-forward networks, different types of data, we want to try to understand them mathematically. We want to prove theorems about them, and that's sort of the heart of the theoretical activity. We understand these deep networks, and in particular, in this context, we understand deep representation learning by trying to prove theorems about these objects. And I think that this is very important as kind of an ideal, a high-level goal for what we should be trying to do around the theory of deep learning. But I can tell you from a lot of personal experience, and maybe hopefully in the audience, if you've been there too, you'll agree with me, this is a very challenging activity. And despite maybe in the last 6 or 7 years or so, immense investment on the part of money, grants, as well as graduate student lifetimes on these problems, trying to understand, develop theory of deep learning. We've made very little concrete progress on these general questions of understanding deep representation learning for data that is kind of like what we're observing and processing in the physical world. We make a lot of progress on restricted special cases, networks that are very shallow, not deep, the opposite of deep, in fact. Data models that are very unstructured. They don't have a lot of low-dimensional structures that match what we see in the real world. And even though this leads us to very interesting, rich, compelling mathematical theory, deep questions that one can even study further and further, it hasn't really, I don't think, and maybe in this case, I just speak for myself and my own personal research experience, it hasn't really shed much light on this general, important, compelling question of how do deep networks really learn representations for data in the real world. So in this talk, we're kind of going to come at this theoretical question from a slightly different approach. Maybe I just say different, both in contrast to this top-down approach and maybe different from my own sort of the approach I would take on these problems before, which is a little bit more of a bottom-up approach. And so this is sort of a very crude characterization here. But what I mean by bottom-up is that we're going to use the theory here more as a tool to kind of guide our intuition, use the same sorts of models for deep networks and data, not as sort of a core essential mathematical activity in itself where we're trying to prove theorems, but just to guide us for thinking about what are deep networks doing when they compute with data that has certain low-dimensional structures, like Yi talked about in his talk. In particular, maybe using these theoretical models just in order to understand what are the important problems that kind of unify across different applications, tasks, data modalities, what have you, what we're trying to use deep networks to do to learn representations for high-dimensional data. So using the theory as a tool to maybe identify important problems that we can then understand at various levels of rigor and get some insights in order to maybe design better deep network architectures. For example, they could be more efficient, more interpretable in certain settings, which could have very useful practical consequences. So I'm calling this bottom up just in sort of the way that we use the theory in order to make a connection to practice. And like I said, in this talk, we're going to mostly come at things from the latter. In particular, we won't have any theorems in this talk. So kind of as a high-level guide for what we're going to be talking about in the rest of the slides, I want to try to pose, with this theorist hat on a little bit of a model problem that I want to use as kind of a way to frame deep representation learning in general, really what this problem is all about at a mathematical level. And by the way, I hope that if you have any questions throughout the talk, feel free to interrupt me and we can discuss them in real time. So this model problem, I'm going to refer to this as compressive autoencoding. And what this is about is, so given some high-dimensional data X with low-dimensional structures that I'm going to leave sort of vague for now, I want to learn a representation. So in particular, I want to learn an encoder, F, some mapping from the high-dimensional space to a lower dimensional representation space, giving me a Z. Z is equal to this F of X. Let's say sort of in the autoencoding framework, I also want to learn a corresponding decoder G so that I can reconstruct the original data distribution in some suitable sense from this learned representation Z. And this problem, it would be ill-posed anyways, but as I've just stated it now, is especially ill-posed. So in particular, we want to make it better posed. And of course, this is important for representation learning in practice too, by adding a few additional desiderata that we want whatever representation Z that we learn to satisfy. So we're going to summarize this here as just three sort of simple principles. We want this representation Z to be compressed. We want it to preserve only the intrinsic low-dimensional structures in the input data distribution X. So compressed, we want it to be linearized. So in particular, even if the input data distribution X has highly nonlinear geometric structures or otherwise, we want those corresponding structures in the representation space to be linearized so that we can use this representation to do very easy downstream processing of the input data X. For example, if we're trying to do grouping or tracking or segmentation, what have you, it's useful to have linearized representations for doing interpolation, extrapolation in the representation space of the data. And the last condition, we also want this representation to be sparse. And so I'm using sparse here in kind of a slightly generalized sense that encompasses a little bit of the incoherence that Yi was talking about in his talk just now. So we want the representation Z to be both sort of made incoherent in some sense. So if you have distinct factors of variability in the data distribution X, you want those to be made incoherent, maximally uncorrelated with each other to the extent possible in the representation space. And you also want the representation itself to be sort of having a small number of non-zero entries, so sparse in the traditional sense as well. So the two of those conditions together, I'm going to call sparse. So these three considerations, together with learning an encoder F and a decoder G, I'm going to call satisfying all these conditions a compressive autoencoding problem. And I'm claiming that this compressive autoencoding problem here is actually a very good sort of summary for all of the deep representation learning we're doing in practice. And so that might be slightly contentious. The way I'm seeing it is just that, so even though in many cases in practice, we don't truly learn a decoder G to reconstruct the data from the representation, in many cases in modern deep learning, because we're working with these extremely large-scale foundation models, where we we learn the representation on such a simple pretext task with such a large-scale model that we're actually able to use the resulting representation to solve many different distinct downstream tasks. To the extent that it's reasonable to expect that that representation is sufficiently informative to be used in principle to reconstruct the input data distribution X. So that's the sense in which I'm seeing this as kind of a universal summary or formalization of what we're doing with deep representation learning in practice. And I want this to kind of guide all the thinking that we're going to have for the rest of the talk. And so in particular, first I want to describe three sorts of very common modern representation learning, representative, as not common, representation learning frameworks. I want to describe their sort of strengths and weaknesses, sort of as a preamble to the kind of unifying approach that we're going to develop in the rest of the talk, following on from the ReduNet approach. So first, I'll talk for a little bit at a high level about transformers. So we're going to talk in a little bit more detail later on, just to summarize the mechanics of this network architecture. So I'll just talk at a high level right now. But transformers have become extremely popular as kind of a universal backbone architecture for representation learning across a lot of different data modalities and tasks. So in particular, they've started being extremely successful in natural language processing. They've gone on to also be useful in many different vision foundation models. And they're even being used in more diverse applications now as well. So this architecture seems to be truly universal as kind of a backbone for doing representation learning at very large scale. So what's the problem here? I mean, no problem, right? You can do so much with transformers, but one thing that's a little bit lacking here, especially in the context of trying to understand architectures that are satisfying for this compressive autoencoding model problem, is that transformers are black box, let me say a little bit more precisely, like empirically designed neural network architectures. So I'm not disputing that an immense degree of engineering know-how and even at some level engineering principles have gone into the development of this transformer architecture, over many 6 or more years. The different blocks in the architecture are totally empirically, battle tested, and it's through the effort of the massive, deep learning, machine learning community that we've actually been able to arrive at this architecture and haven't seen so much success. But what I mean by empirically designed here is just that the reason that we're using the layers in the transformer, the operators in the transformer, and maybe the architecture itself, it's really just based on performance considerations in practice. Things like an architecture that can be used, scaled up very well with large amounts of labeled, unlabeled data. An architecture that can be deployed very efficiently on different hardware platforms, used very fast for inference, training, what have you, at the largest of the large scales. So it's not the case that this architecture has been designed the way that we designed a much more simple representation learning framework like dictionary learning in the past. And that can have important consequences. So, for example, some of the very interesting behaviors that we've seen emerge from transformer training, they're totally unrelated to things that we seem to have asked for in training throughout this conference. So, for example, in Bin's talk, we were hearing some theory for this in-context learning framework. We can also see in certain applications, it's possible under a very interesting concoction, witch's brew of different self-supervised learning frameworks and training tricks for the representations in certain trained transformers to actually carry highly salient, useful semantic information about their inputs. But why those properties emerge, why this sort of in-context learning ability emerges from the training, it's very hard to understand that because the transformer architecture is kind of empirically designed, black box. We need sort of a different type of representation learning framework, one where the representation is actually itself better exposed, the properties it has, in order to more easily understand phenomena like this. And even on the theoretical side, there's a lot of competing interpretations for what the transformer architecture is trying to do. These interpretations, many of them, they give very interesting insights into kind of the operators that compose the transformer architecture, explaining some of them in different parts, isolated special cases. But none of them have really in a unifying way, help to understand what is going on with this network architecture. So there's a lot there to be desired that we'll kind of try to resolve a little bit, at least in this talk. So in addition, there's important consequences of using black box models on important practical considerations like safety as well. So when you don't understand the representations and maybe the internal mechanisms of these transformers, of course, there's lots of post hoc work you can do to try to enforce safety or understand these representations better. But it's very hard to guarantee safety with a black box model. So transformers with this kind of empirically driven black box design are a little bit suffering here, and there's room for improvement, let's say that. So if I go back to kind of the compressive autoencoding framework, just to summarize briefly, what we're seeing is that in spite of all the impressive practical successes of transformers in the modern machine learning landscape, the fact that we have this black box design means that in this framework where we want to have the ability to learn representations, where we have certain baseline understanding guarantees of properties that the representation has, being compressed and sparse, what have you. Maybe the transformer is learning representations that are compressed and sparse. In fact, because they're useful for so many downstream tasks, it's sort of reasonable to believe that it is. But this black box design makes those representations completely inscrutable to us. We cannot figure out these properties a priori without a lot of detailed and sometimes not the most principled kind of work just to try to figure things out on an ad hoc case-by-case basis. So this black box design is holding us back here with regards to this representation learning desiderata. So let me switch gears slightly, talk about kind of another end of the spectrum of modern representation learning architectures. And so this is kind of a representation learning framework in a loose sense. I'm talking about diffusion models here, which are powering a lot of very exciting, cool, modern generative AI applications. So diffusion models at a very high level are learning kind of an implicit representation for high-dimensional data distributions by learning to transform the data distribution into Gaussian noise, and then incrementally at many different scales, learning to denoise that noisy data distribution. And by a certain way of combining those noisy representations, noisy intermediate representations, in particular using this special function called the score function for the noisy data distribution, it's possible then to transform the data distribution, the high-dimensional data distribution, to and from structured Gaussian noise, which is very easy to sample from. So we can use diffusion models to sample from very complex high-dimensional data distributions. So everyone, I'm sure you've seen videos better than this. This is just some very simple for these modern latent diffusion models to generate truly photorealistic, very impressive, at least to me, natural images, things that would have been inconceivable with sort of the dictionary learning-based past representation learning methods. So this is extremely impressive, but there's still some limitations of these diffusion models with regards to thinking of them as a framework for representation learning. So in particular, the way that we actually in practice use this diffusion model kind of try to control it. So do controllable sampling, like generating these sort of Dutch Renaissance style still lifes of grapes in a basket that I have on the slide here. We use these cross-attention operators in the UNet denoising neural network architecture to condition the neural network, to condition the denoiser on text data that describes the image I want to generate. The reason we have to do that is because the diffusion model a priori just transforms this complex high-dimensional data distribution to a Gaussian noise, a completely unstructured representation. So it's just Gaussian noise in kind of the same dimensional space as the data distribution itself. So that representation, it's really just an implicit representation for the data distribution, and it's totally unstructured. So that makes it challenging to really understand how to do this control in a very scalable, generalizable way, even though we can achieve very impressive kind of results on the internet. There's also a question of what types of operators one needs to use here in order to learn the diffusion model. So what types of neural network architectures in particular. So what we're actually doing when we implement the diffusion model is to represent the score function. At the heart of the diffusion model is the neural network is being used in this sense to parameterize the score. And for complex high-dimensional data distributions with very strong mixed low-dimensional structures like natural images, it's not always clear what the sort of the structure of neural networks should be used to parameterize these score functions. Even though a lot of progress has been made, just like with transformers, via, trying very numerous different designs and keeping what works. One kind of wants a more principled understanding here of what are the right sorts of operators to use to parameterize these high-dimensional data distributions. So again, going back to the desiderata, diffusion models, in spite of their successes, from the perspective of learning an interpretable, useful, compressed representation for the data, they are falling short because the representation that we get from a diffusion model is only implicit and it's completely unstructured. So in particular, we want our representations to be linearizing, compressing different distinctive structures in the input data. So finally, it's kind of the third alternative and the counterpoint to these more empirically designed architectures. We have sort of white box, I'm going to call them white box models in the talk, like the ReduNet that we just heard about in Yi's lecture. So the ReduNet is kind of doing something different, of course, from an empirically designed neural network. It's using a neural network that's explicitly designed to kind of represent and pursue certain low-dimensional structures in the representation. So what that means is that when you're using a ReduNet to learn a representation, you're kind of by default learning a compressive encoding of the data, just because by design, the network has been set up to seek such a representation for the data distribution. But like E alluded to at the end of his lecture, there's still some sort of gaps to close when it comes to white box models like the ReduNet. The biggest one is how to obtain very strong kind of performance measured in different ways, and also efficiency, the ability to use these models at large scale, so sort of high resolution photorealistic images, what have you. So previously, this has been very challenging with white box approaches like the ReduNet and maybe other similar approaches that have appeared in the literature. And another question here that we'll come back to a little bit in the talk is ReduNet is allowing us to obtain kind of a compressive encoding of the data, this representation Z, but it's not exactly clear in the ReduNet framework how to construct the corresponding decoder for the input data. Even if we have a very expressive, compressed and linearized representation Z, because ReduNet is sort of, and we'll review this later on, designed in terms of the rate reduction objective, which is measuring the quality of the learned representations. We don't really have another corresponding objective function that tells how to go backwards from representations to the input data. So that objective is solely about the representation. So how to obtain a corresponding decoder, this has kind of remained an open question around the ReduNet. So what we're going to talk about today, now that we've summarized these three different very popular representation learning approaches, transformers, diffusion models, white box models like the ReduNet, we're going to kind of try to unify, meld a little bit ideas from these three different representation learning frameworks so we can obtain an architecture, a representation learning framework that we can use to solve this compressive autoencoding is working, showing promising performance at scale, and is also sort of white box. So we understand the learned representations of this model and can use those to solve many different downstream tasks. So that's where we're going for the rest of the lecture. Just a quick outline. And I want to try to spend a little bit, a good amount of time on the basics here. So I'm going to summarize the rate reduction framework from the last lecture a little bit and talk about three key changes that we need to make to that rate reduction objective in order to get kind of a different, slightly modified, very related, but slightly modified objective function for measuring the quality of learned representations. It's going to be sufficient for us to derive this crate architecture that I'm then going to talk about next, this white box transformer crate. So I'll talk about the objective function, I'll describe the derivation of crate, and then I'll show some experimental results showing that this model has very promising scaling behaviors, interesting interpretability consequences as well. Any questions about the framework before that? Yes. 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 Right. No, it's a very good question. So I would say that when I think about the transformer specifically, so I don't say that the transformer representation is unstructured. Indeed, I completely agree with you. There has to be some nice structures there. We just don't necessarily know how to reveal them. So I think there maybe are methods that come from the interpretability literature, maybe the mechanistic interpretability literature. They could be used to try to reveal certain properties of those structures. At the same time, I know there are some critiques, although I'm not an expert. There are probably some experts in the audience here. There are some critiques of those methods in certain cases. People are saying that maybe sometimes they are showing you what you are looking for or something like that. So I'm just saying that from my perspective, and very much this bottom-up perspective, the way I see it is that it makes more sense just to try to design an architecture that has interpretable representations or structured representations from scratch. So of course, you'll need to do some hard work to do that, but that's what I'll talk about in the rest of the talk. So does that make sense? So I agree with you about the transformer. I don't exactly know how to reveal some of those structures.
Yeah, okay.
And so instead, we'll try to do this bottom-up construction. Yeah, very good question. So let's talk about the framework then. So let me just recap kind of this lossy coding rate function. And in particular, I want to talk about the delta R, the rate reduction objective that we use to derive the ReduNet, just so we can make a contrast. So we're going to denote, as we have been now, the representation here, capital Z. So this is just a collection, maybe of data samples, so samples here. Each column of this matrix Z is maybe a different sample from an image distribution or something like that. And in this setting, the maximal coding rate reduction framework, we're going to assume we have labels for the data as well. And so I'm going to encode the labels here in these matrices pi. So this is a setting where we have k different classes, and these pi matrices are diagonal one-hot matrices that kind of denote the membership of the different samples into each of these k classes. Then we can define these different functions that are associated with the rate reduction. So we have this approximation R for the lossy coding rate, which, as E talked about, we can interpret this in many different ways. It's kind of like in one statistical interpretation, measuring kind of the cost to represent at a certain level of quantization, the data distribution that's kind of encompassed by Z in terms of a single kind of Gaussian model. So that's one interpretation. There's also connections to volume sphere packing as well. Then we also have a slightly more refined notion of compression, this RC term, which is measuring this approximation for the lossy coding rate when you like individually separate the different data samples according to the different classes. So this is the cost to code each of the individual classes separately. And the rate reduction is just the difference of these two metrics. So we know from Yi's lecture, from Yao Dong's past work, that there's this nice principle associated with this rate reduction objective, which comes from the fact that we can characterize its maximizers under certain pretty mild conditions. So those maximizers correspond to, like, if I drop from the compressive encoding framework that I've been talking about, the sparsity requirement, the third one. So those maximizers of this objective function correspond to compressive encodings of the data. So these encodings are kind of compressed and linearized. So in particular, like at the intuitive level, these representations are preferring to kind of separate the distinct classes in the data distribution into different incoherent subspaces, which take up as much volume as possible in the representation space. So the ReduNet is really using this maximal coding rate reduction principle by constructing a neural network to optimize the rate reduction. It is seeking to represent the data in terms of one of these optimal configurations of that function. Okay, so that's the rate reduction as we've used it for Redu. For our purposes in this development, we're going to need to make 3 modifications, and I'll talk about them in sequence here. So these 3 modifications are, instead of processing the data as samples like we do in Redu, we're going to process it instead as kind of a sequence of tokens. That's like how the transformer processes data, and we'll talk about that next. We're also going to add an explicit model from the data for the data distribution into the objective function. So that will allow us to be a little bit more flexible in the representation. And then we're going to explicitly enforce that the representations are sparse. So this is going to give us something that we'll call sparse rate reduction, and we'll use that to derive the crate architecture. So first, let me recap kind of how the transformer is working and how the transformer is maybe processing images. So I'll talk about this in the context of visual data here. So the difference between maybe something like the classical CNN that ReduNet is kind of mirroring and the transformer is that the way that the image is processed by transformers is that you take this raw image and then you split it up into non-overlapping patches. So kind of like in the figure here. Then you take each of these patches, you flatten them, and you stack them into a matrix. And now that matrix is going to be our new capital X, so sort of the data. Instead of capital X corresponding to a bunch of different samples, it's going to correspond to all the different flattened patches from one natural image. So then the transformer processes this sequence of flattened patches by a series of two operations. The first is sort of a tokenization operation, which is just a linear embedding of this patch matrix, or this matrix of flattened patches. So we also add this class token that we'll use in sort of experiments. But this is sort of, sorry, not linear, but affine. And so in particular, we have this positional embedding that allows to inject some information about where the patches are in the image into the transformer architecture. And that's very important for its correct functionality. So once we tokenize, we just process the data with a bunch of identical transformer layers. These layers have a pretty simple structure. They correspond to interleaving something that's called the multi-head self-attention operation and multi-layer perceptrons, just a simple two-layer MLP, together with suitable normalization and skip connections. And if you haven't seen it before, this self-attention operation is sort of like an interesting way to sort of rescale the different elements of the sequence based on their correlations with one another. So this softmax is doing some normalization along the columns of this matrix of correlations. And we have learnable projections in the self-attention layer. So these learnable projections, as well as the parameters in the MLP, are going to end up corresponding to the trainable parameters in this transformer architecture. So the insight we just want to take away here is that transformers have been really successful at processing different modalities of data as tokens. And so we're going to apply that in our model as well. So we're going to, instead of calculating rate reduction on batches of images, we're going to calculate it on sort of a token representation for a single image. And then the sort of functional form is going to be exactly identical to how it was before. That's going to allow us to learn interesting correlations between patches within a single image and sort of, in some sense, for image data, and for example, kind of linearize certain transformations, allow us to more easily represent certain transformations of the image. So as for modeling the distribution of the data in the objective function a little bit, so we're going to take some insight from a lot of prior works, especially inspired by some of this prior work on the sparse land framework, and explicitly try to model the distribution of the data in this objective function. So we're going to do that in a pretty simple way, which is just to posit a very simple statistical model for the marginal distribution of the tokens in our desired representation. So in particular, we're going to posit some subspaces, orthonormal bases for subspaces UKs. We'll have capital K of those. And then we're going to seek to enforce that the learned representations, the representations that we're learning, are distributed such that they have marginal distributions for each token, which are a mixture of Gaussians that are supported on these distinct subspaces, if that makes sense. So these marginal distributions are just simple mixtures of Gaussians, and the parameters here are the different subspaces. So we're using these subspaces kind of like a learnable dictionary in order to represent the data distribution. And so here, we're not placing very many constraints on the joint distribution of the token. We're not placing any constraints at all on the joint distribution of the tokens. We're only asking its marginals to satisfy certain properties. And in general, So it's not going to be feasible to compute exactly what even a tight approximation for the coding rate is for that token distribution according to this model. What we can do is, because we're enforcing that the marginals have this specific supports, we can always compute a simple upper bound for the coding rate, analogous to our compression term previously, which simply projects those token representations into each of the subspaces and then calculates their coding rate according to the same approximation of those projections. And then we sum those up. So that's the approximation we'll use. And then together, so combining this with just calculating, just like before, the approximate coding rate for all the tokens at once, we can arrive at a suitable notion of delta R that will be working better for our purposes here. So the difference here compared to the previous delta R is that now we've kind of, the role of the pi matrix of labels that we had previously is now being played by these learnable subspaces, the UKs. So finally, to enforce sparsity, and we want to enforce sparsity here simply because there's a sort of an obvious rotational ambiguity that's associated with the model as we've constructed it so far. So in particular, if you simultaneously rotate the tokens as well as the subspaces, you will get a configuration that has exactly the same rate reduction as we've defined it. So in order to kind of quotient that out, have a more convenient and sparse in the natural canonical basis representation, we can simply enforce sparsity in addition to optimizing delta R in this objective. So since we're eventually going to do maximization, we'll subtract off the L0 norm. Just conceptually, this is measuring sparsity. And what we get here now is what we're going to call the sparse rate reduction. So the sparse rate reduction, intuitively, we should expect it by its close parallel with the rate reduction. Although this is kind of the subject of interesting ongoing work, we should expect it to also satisfy kind of a maximal coding rate reduction principle. So in particular, if we can maximize this objective function, we'll obtain representations that satisfy our desiderata for compressive autoencoding. So that's going to be enough for us. We can proceed with this sparse rate reduction, and we're going to now derive a transformer-like architecture from maximizing this sparse rate reduction in a certain way. Any questions?
That different UKs are orthogonal to each other?
Do we assume? In this statistical model, I have asked them to be orthogonal to each other. Yes.
And that's why you can take UK transpose C to get out the coefficient under this basis.
So I think in the framework as I presented it here, I'm just sort of talking about definitions here. So I may be missing the question, but I think that so far I haven't committed any sins. Down the road, if we want to do certain analysis, this may be a problem that we need to contend with. And one thing we'll look at is actually, so is this assumption that we've made verified in practice? We'll see that indeed, in many cases of interest, it is. But sorry, go ahead if it.
No, thank you.
Okay. Yeah, we'll try to address that one empirically. Yes.
One question.
Yes.
So then, if I understand correctly, the role of those subspaces is to compute the rate reduction.
Yes.
At a lower dimensional ambient space without losing anything. We're really computing the rate reduction for a given class. Right? Is that it?
I think that's one way to think about it, but the problem is that in practice, these UKs may have correlations themselves. Although, as Tinjao said, we want them to be maybe incoherent or even orthogonal. So I mean, I'm sorry, maybe I misinterpreted the question. I want these UKs to actually be like from the CPAL manifold, but I may also want them to be incoherent to one another or orthogonal. I think I haven't asked them to be mutually orthogonal yet, but in many cases, we do want them to be so, to have what you said, I think, actually obtain, if I'm following correctly. If those have correlations, then to truly calculate the coding rate on those projections, I think that would become intractable.
I'm asking something slightly different.
Oh.
So, in USOC, we did
Yes.
have the
No.
UK, right?
Yes.
Okay. Now we have them.
Yes.
Those projections, they are orthogonal projections, so we
Yeah.
should give them orthogonal projection.
Yeah.
And if the K class is of the form UK times of alpha, then the norm is preserved. So, so we're measuring the rate reduction at the smaller dimensional space,
Yeah.
the image of the UK,
Yeah.
right?
Yeah.
And we don't lose anything. That's my question. Is that it? So
Right.
we have the data from the case class sitting in a big dimensional space. And then we project them. And then we compute the rate reduction. So in other words, does the computation of the rate reduction commute with the projection? That's my question.
So in the reducer, the reducer in the sense of with more simplified assumption, the data can be separated. And we're making them simple and transforming each classical subspace of them. Here, this subspace is slightly different. This is actually only measuring, projecting the joint distribution in Z, and into the different subspace and measuring those coordinates in those subspaces. You can see about this kind of code book, but we're not making much assumption on what is joint distribution. So hence those coordinates, the code is kind of upper bound on what we could record. If the coding is invertible, okay, if there's enough subspaces, projecting Z onto enough of them, and I compute the coding some amount, that's kind of upper bound for how should I code the data. But of course, you assume that users are not too redundant or you are relatively phone to minimize the redundancy. So you can see about this is already a more relaxed setting. And of course, we're going to use this coding to guide how we transform distribution, underlying joint distribution. But there's no strong assumption what will happen to that joint distribution. And yet for future to figure out for what type of joint distribution this kind of coding, this kind of transformation is going to do to the distribution and have some new additional nice properties. So that's still open.
Yes, I think we can continue to discuss this after all. It's an interesting question. Yes.
So for this floating rate reduction, I think some people are talking about information bottleneck in this conference.
Yeah.
And the idea there is that instead of like explicitly compute floating rate and reduce it with gradient, we can just look at reverse the neural network as a channel and reduce the thing like within the noise. So do you think that kind of idea will achieve something similar to this?
Yes, absolutely. If I understand the question correctly, I think this type of idea, so I'm not necessarily sure the connection to the information bottleneck, but definitely when we go to drive the network architecture, as far as the block, we will be taking gradient steps on certain parts of this event. The question is just, always, you want to design an architecture of optimization. How do you choose to optimize this object? Like he said, you have, all 300 years of optimization history kind of able to test. You can use it in various creative ways to design whatever architecture. So we'll do something that's very simple for the rest of the talk, but it will be a little bit of this. Does that address the question, or is it more specific to the information problem?
Well, I'm just saying that there might be some another approach might address some similar problems, and I'm just thinking whether what's the relation between this algorithm and the information model.
I see.
And I think one advantage there is that it's much simpler because that's into a noise. It's instead of like it's pretty easily like compute this order rating and platform it.
Yeah, I'm not sure. So maybe we can take it offline. But I'm going to say the information bottleneck is that it's easy to define in terms of the task. And so here, we're really thinking of this in terms of learning representation satisfies certain things. So the notion of the task hasn't actually been present here. And that flexibility, I think it is desirable in many ways. But we can discuss it more offline to understand it better. Okay, by the way, I think I'm talking a lot. We were sort of off schedule starting maybe we can clobber the coffee break a little bit. Is it okay, or what do you guys think? Yeah. So let me move on then, in the interest of time, and start talking about the transformer, this white box transformer, so-called crate, that we define now by a certain unrolled optimization on the sparse rate reduction. So crate is going to be our sort of promised white box, mathematically interpretable, neural network architecture that's kind of like a transformer, because we've now processed data as a sequence. And we'll see how it becomes a transformer via the optimization of this sparse rate reduction objective in a pretty interesting way. So just recapping, we're going to kind of separate this sparse rate reduction objective that we've defined into two different parts. We're going to isolate kind of the compression part, this RC term, which is measuring how compressed the current token representations are with respect to these subspaces UKs. And then also a sparsification part that splits off the expansion term, which is just measuring the coding rate for all the tokens, and with the difference of the sparsity. And so when we actually optimize this thing, we'll talk about it more later, but of course we're going to relax the L0 norm and optimize sort of a convex relaxation for that. But just for conceptual purposes, we can think of just that sparse promoting regularizer there. And so the way we're going to construct the representation, just like with Radu, just like with deep networks in general, we're going to do it incrementally, but in the context of unrolled optimization, and in particular, this sort of unrolled optimization of a representation learning objective, this incremental construction kind of takes on an interesting significance here, which is that when we go to train this unrolled model, learn the parameters of this model. So as we posited it so far, those parameters are going to be the subspaces UK for each of the different layers. And since those layers are going to have generally untied parameters, now we're learning different subspaces for each layer in the network. So you can interpret this resulting unrolled constructed, this sort of incremental, sort of incrementally optimized representation as doing repeated kind of iterative processing of the data distribution against different variable local signal models. So I'm thinking of these UKs as being models for the data distribution at each layer. And the fact that those are changing from layer to layer means that we have the potential and really the chance to model significant nonlinearity in the data distribution. So even though at each layer, we're going to just be doing a small optimization of this objective function around the current representation, the fact that we can adjust the parameters of the model from layer to layer, just by the unrolling framework, and we'll talk about it more, but that's actually allowing us to design a representation for the data that's very flexible and sort of incrementally transforming the highly nonlinear, mixed structured input data distribution towards the desired compressive encoding of the data. So the question then that we need to answer here is what strategy we're going to pick to optimize this objective function incrementally. So like I said before, we're going to do something that's arguably simple and naive, just the most basic approach to see what can be accomplished here. And we'll see that there are already some interesting consequences on the practical side. So first, what we're going to do is just take a gradient descent step on the compression term of the objective. And okay, we're not going to do gradient descent. We're going to do something that we'll call approximate gradient descent, which is to take a gradient descent step on sort of an approximation for the gradient at the compression term. So the approximations are here just being made out of convenience, sort of computational convenience, because ultimately here, the way we were seeing this unrolled optimization procedure is a little bit in a little bit of a looser sense compared to maybe the most traditional, the most stringent interpretation of unrolling, where you're trying to obtain an architecture that might directly inherit certain mathematical properties of the underlying objective function that you unrolled and the solver for it that you used for the unroll. So in particular, things like convergence guarantees or things like that. The notion of unrolling that we're thinking about in the design of Crate, similar to the design of Radu and other white box maybe networks, is that unrolling here, optimization here, is sort of a tool for designing the architecture. It's a way to get inspiration for the different ways to design the architecture. And ultimately, what determines whether or not we've done a successful unrolling in this sort of paradigm is when we go to evaluate the learned representations, do they truly optimize the objective function that we designed the network to optimize? So we'll test that empirically. We'll sort of work on the empirical side here and verify that indeed any approximations that we make are sort of justified in that sense. But so after we make those approximations, the surprising thing here, and E alluded to exactly those approximations that we're sort of making under the hood here at the end of his lecture. But we're getting an operation here that's like very startlingly similar to the self-attention operation, in particular the multi-headed self-attention operation in a standard transformer architecture. The difference, if we contrast to what we saw before, is that here, the QKV, query key and value projection matrices in the self-attention layer, they're all the same. And they're all set equal to these different subspaces in the local signal model for the data distribution. So we end up, by taking this gradient descent step on the compression term here, this approximate gradient descent step, getting kind of a self-attention-like operation. So this sort of local incremental compression is giving us a self-attention operation in the architecture. And if we visualize that in block diagram form, and in particular, make a certain choice of the different parameters in the model, the step size, we will get a block that looks like this. And of course, introducing suitable normalization, just like in the transformer. So as for the rest of the objective, now to sort of continue or finish the optimization, we need to optimize the sparse part of the objective. So to do that, we'll just posit kind of a very restrictive way to optimize the objective. So we'll just introduce orthogonal dictionary and try to sparsify the current iterates of the representation. So after taking that incremental step on the compression part of the objective with respect to that dictionary. So because the dictionary is orthogonal here, the expansion term isn't playing a role in the optimization. And approximately, so we can sort of relax the resulting optimization to be sort of conceptually the following simple constrained convex, the following constrained optimization problem, just seeking to sparsify with respect to this learnable dictionary. So this dictionary is going to become a trainable parameter of the model. And in order to sort of tractably solve the previous problem, we'll compute the Lagrangian relaxation and then also relax the L0 norm into the L1 norm. And this is going to give us sort of a lasso type problem. Optimizing that with a single step of gradient descent, so again, just working totally locally, is going to give us an operation that's like a soft thresholding step after taking a certain linear projection of the data. So again, that's just like the kind of one iteration of the proximal gradient descent algorithm from optimization. So that gives us a block, we'll call it the ISTA block by its similarity to the ISTA algorithm, which is sort of sparsifying the data with respect to this learnable dictionary D. So in our implementation, we'll further ask here, just for sort of performance reason on classification, for the data to be, instead of using the L1 norm, we'll use a sort of non-negative sparse coding. So that will give us a nonlinearity of ReLU in this block, instead of a nonlinearity of the soft thresholding function. So when we view that in sort of a block diagram format, this is sort of what we end up with. And then when we combine those two blocks, sort of applying them iteratively to get an unrolled network architecture, we end up with this repeated compression and sparsification that is encompassing each layer of the crate architecture. Compression corresponding to the multi-head subspace self-attention block, sparsification corresponding to the ISTA block. We repeat those L times in order to generate our final representation. And so viewed as a block diagram, one layer of the crate architecture ends up looking something like this. Very much a transformer-like architecture. In practice, the way that we will learn this architecture, so again, we're kind of separating here, transforming the data towards this desired compressed representation as like kind of a forward optimization that's computed by forward propagation over the resulting unrolled network. We also, of course, want to learn the parameters of the local signal models in sparsifying dictionaries. So in practice, we can do that through any sort of pretext type task that is carrying sufficient semantic information about the data distribution to learn meaningful representations. And in the experiments I'll talk about here, we're going to do that with classification. So comparing the two architectures just at a high level, CRATE is very similar to the VIT architecture, and the key differences are just at a kind of an operational level. In the attention block, the three QKV matrices are all the same. And in the MLP block, Crate is using an ISTA, more parameter efficient sparsifying block. Other than that, these architectures are quite similar, kind of Crate is a transformer-like architecture. So one thing I'll mention only very briefly, I won't get, definitely don't have enough time to talk about it now, but we can actually do full compressive autoencoding in this framework as well. So because of the fact that Crate is kind of, in particular, the multi-head subspace self-attention block is very connected to compressing the data distribution locally with respect to the signal model, we can exploit a connection that we unpack a little bit in recent work between compression and denoising in order to understand that it's possible to kind of very locally, right, incrementally, very close to the target data or target signal model, these UKs. It's possible to invert this operation by using ideas from denoising diffusion in order to derive a corresponding decoder architecture. So I don't have time, unfortunately, to talk about this today, but by this interesting connection between compression and denoising, we are able to also derive a white box decoder with this framework. So I'm running out of time, so let me just talk quickly through the experiments. First, we have experiments that kind of verify the design concept, sort of following Tin Zhao's question earlier. So when we go to train a Crate model, we're going to, so we need to sort of learn these subspaces U and these sparsifying dictionaries D that are actually encompassing the parameters of the model. We're going to learn those by training. So in our experiments, we're just training on classification tasks, kind of in the standard VIT setup using the class token. So we want to understand, after we do this supervised training, do we actually learn representations that indeed, or sorry, parameters, signal models, dictionaries that indeed optimize or verify kind of the design goals of Crate, sort of optimizing the sparse rate reduction. And so what we see in experiments, these are showing for sort of a representative Crate model on ImageNet training, looking at some of these metrics calculated on some held out data from a specific patch, that over the iterations of the Crate model, the Crate model, we actually do see the coding rate decrease by a fairly significant amount from input to output, kind of average as well as the sparsity of the representation improving significantly from input to output. So even though we don't know the true, if there are even true for ImageNet, signal models, dictionaries for the data distribution, by doing this supervised training, we are able to learn parameters that lead to the Crate architecture achieving its design goals here. And we show as well that, so these goals aren't satisfied by the randomly initialized network, and they sort of improve incrementally over the course of training. So doing this supervised training is very crucial here. I'm going to skip these visualizations and talk about one significant benefit of Crate here, which is an interpretability benefit. So what we observe in experiments is that just after doing supervised training of the Crate model, its second to last layer representations, sort of here visualized in kind of a self-attention matrix format, carry significant semantic information about the input data distribution. So here, well, I'm showing that the different heads in the Crate self-attention layer, sort of at the last layer of the network before the class token, or at the class token, are corresponding to segmenting different object parts of the input data. So in particular, different heads across different objects, different classes, are segmenting the same parts. So this is kind of an interesting interpretability benefit that we see emerging from the way that we've designed Crate in terms of pursuing structures in the data distribution, pursuing a compact and sparse representation. You don't need to use any special self-supervised learning tricks or training tricks otherwise in order to see this benefit. So this is kind of a promising benefit of this architecture that I think is kind of speaking to the potential of the white box design a lot. And we show as well that Crate can scale pretty well, scale promisingly. So on kind of after ImageNet 21K pre-training and ImageNet 1K fine-tuning, we can get over 80% top one accuracy with a Crate model. Oh, maybe I copied the wrong table. Sorry if I did. But so maybe this is the 1K table. But so we can get very promising scaling behavior and top one accuracy behavior of Crate with a small fraction of the parameters compared to similar VIT. So we're being more parameter efficient and obtaining pretty nice performance at scale with CRADE. And just as a very brief demonstration, we also are trying to examine that the CRADE architecture can be useful for different data modalities as well. This is not a demonstration of interpretability or anything like that, but we do see that CRADE can be useful for natural language data as well, trained with very small modification in kind of a GPT format here and comparing favorably to a GPT-2 model. Okay, so sorry I go through the experiments fast. I know I'm a little bit over the time now. So I just want to wrap up with two concluding messages. So through this white box design, we see through this white box transformer CRADE architecture, both interpretability benefits in terms of the segmentation behavior that emerges from a very simple, maximally simple training recipe, as well as some promising performance and scaling behavior with better parameter efficiency than equivalent black box models. And I want to echo the message that Yi gave at the end of his talk here, that I think this work, to me, it's really showing that there's a lot of potential here. And using in kind of this bottom-up, a little bit cavalier, flexible way, ideas from optimization, sort of high-dimensional data analysis, as a tool for designing deep network architectures. So we have this compressive autoencoding problem that I've talked about in this talk. It's kind of just a guideline, very simple, general, and yet expressive enough to already give you some good goals for designing deep network architectures that can do very well, surprisingly well, at least to me, on large-scale data sets and with useful practical consequences. So I think the future is very bright for these models, yeah, hopefully you agree. Okay, so thanks for bearing with me through the talk. I really regret that I forgot to include the last slide that thanks all my collaborators for this project. This great work has been a wonderful collaboration with a lot of great researchers. So let me thank in the audience here, Yao Dong, Drew Chenje, Yi, as well as a lot of collaborators who aren't here, especially Ziyang, Ben, great folks on this project. Thanks for your attention. And maybe we can, yeah.
Take a for a short time. Let's take a break, a quick break. How about 5 to 10 minutes? And
Thank you very much. Thanks for your help.
Oh, we are work tutorial. We don't have to be so time strict.
I know, yeah.
Thank you very much.